if variables are very closely correlated with each other and they are predictive variables. So these are my all IVs, right? So they are correlated with each other. Petrol bus taxi is correlated, school fee, tuition fee, education is correlated with each other, right? You can see that. Now, if there's such a high correlation, what can I do? There's a simple thing that I can do, and that is I can do fact analysis, reduce this. Okay, I will first do the statistical part of it, and then we'll go to the actual fact analysis part of it, right? Okay, so we'll do the actual fact analysis theoretical discussion slightly later. First, see how to do, and then we'll understand the in-depth understanding of fact analysis. Uh, so, is everyone here? Everybody join so that we can start the discussion. May I again request you to keep your videos on. I'm sharing the screen, going to R code. What I'll do is I will write R codes and I'll share them on in your chat so that you can also use them. Okay. Uh, let's start. One of the easiest thing that I can do is to call a package called library, uh, uh, a package in a library called Sci. Okay. So I've called the library Sci. Right. Now, there's a very interesting function in this library called KMO. What is the name of my data? Name of my data is data. So the overall KMO is 77. It's a great KMO, but there's a problem. See, the correlations are between food, oil, fruits, the independent variables, right? Now, first thing I need to do is to make a data frame of independent variables. So I would do new data frame and I'll call it data 1. Okay, data dot frame, and in this data frame I can put things. I'm just copy pasting it, but not putting, instead of plus signs I'll put comma. So all these variables are going to make a data frame. So this is the new object I'm creating, data 1. So I'm putting hash and writing the information. Data 1 has only variables for FA, fact analysis. So I want to run factors on these variables, right? So these variables I've made a separate data frame of these variables and stored it as data one. Okay, so this is what I have done, and I will do Kemo data one. So I'm pasting the command in the chat box for you. Look at the Kemo. These are the Kemo values that we have found. If things are not clear, I'm pasting them for you in chat box. You can copy them and see. Yeah. Okay, you would realize that overall KMO is great. Okay, overall KMO is great. 7.2 is not bad. Variable wise KMO is also not bad for any variable. The KMO value of 0.5 and below is considered poor. A KMO value for doing fact answers 0.5 and below is considered a poor value, right? Now, none of them are 0.5 and below. Okay? None of them are 0.5 and below. All of them are above. Now, why so? The idea of KMO is very interesting, and you should know that idea so that you would understand uh, why 0.5 is so important. Okay. No, इसमें नहीं है. Can you see the screen? Blank white screen.
Yes, sir.
Okay. Now, this animal KMO is to usually what it does is you take summation of R by summation of R plus summation of RP, partial correlation. Okay. Now, what usually will happen? Suppose there is one variable x1, there's another variable x2, there's third variable x3. Okay. Now, if I compute correlation between x1 and x2, partial out for x3. Okay. Is x3 correlated with x1 and x2? No, there is no overlap. Right. So this correlation is a partial correlation. This will be equal to R x1 x2. That is in this case R x1 x2 will be equal to R x1 x2 adjusted for x3. Right? Adjusted for x3. So it means that this value will be, in this case, exactly as R. So R divided by R would be what you get, right? So the point is, as we get a smaller value, whereas RP would be exactly equivalent to R, in that case, we will get a value exactly 50% of the original value, right? So this would be double this value, which would cause a trouble, whereas in other cases, it will be fine. And that is what is informed by K, right? And this thing is what we look for. So a KMO above 0.5 is what we look for. We have got it. Now there is something called as Bartlett's test of sphericity. Okay, let us try to do it. Bartlett.test, and then I will say data 1. Oh, it's a homogeneity of variance. I would perhaps look for Bartlett in psych. Okay, so here I'll go package a psych, or what I can do is I can look for psych. Let's look for psych. Click on psych, and I'll check if there is a Bartlett's test here. Psych core test dot Bartlett's test is the function that they have. Core test dot Bartlett's test R. What I have done is I've just copied it, not Bartlett's dot test. Yeah. And R is equal to core into bracket data 1. Right? This is the Bartlett's test. This is the p-value that we are interested in, and this p-value is significant. I need not write rest of the things. These are default parameters of Bartlett's dot test, so I can still run this without writing them. Okay, I'm keeping them for your information. So I've done these two tests on the data, and I'm pasting them in the group so that you can run. Okay, now this is significant, which means the null hypothesis of Bartlett's test is something like this. They must have given, but I'll tell you that population correlation matrix is a null matrix or identity matrix. That is, all of diagonal entries are 0. That there is no correlation in the population correlation matrix. In sample, what correlation we see is a by chance existence. That is what the hypothesis is, right? This hypothesis is rejected. The p-value is very small, and chi-square value is really large, so this hypothesis is rejected, right? Which means that population matrix has some good correlation, right? Now, if Bartlett's test gives you a significant result and KMO are greater than 0.7, you can do factor analysis. These are the two conditions. Okay, KMO tells you that there is enough of common variance. KMO stands for Kaiser-Meyer Olkin index. It talks about adequacy of the data of the correlation matrix for doing fact analysis. It's also called sampling adequacy test. So we can perhaps use these two parameters to decide whether we should be doing fact analysis or not. So both have clearly indicated that we can do fact analysis, right? Now, how to do fact analysis? There is a function called principal.
Vivek, can you
Yes.
just repeat the second rule of Bartlett's? What is that about? I did
Okay,
not get.
Bartlett's, I will write here. Yeah. What Bartlett's does is you have a null that sigma, which is population correlation matrix, is equal to identity matrix. Now, what is identity matrix? Suppose I have three variables, A, B, and C. A, B, and C. A will have a correlation of 1 with itself, B will have a correlation with itself, and C will have a correlation with itself, which is 1. If I say that B does not correlate with A, C does not correlate with B, C does not correlate with A, then this is what I expect as a result, right? This matrix is called identity matrix, right? This matrix is identity matrix, where unities are in the diagonal, ones are in the diagonal, and all off diagonal values are zeros. This is called identity matrix. The null hypothesis of Bartlett's test is this population correlation matrix. Now, the correlation matrix that we are looking at is based on 200 people, right? But if we take entire population into account, the correlation matrix, which we are calling sigma is equal to identity. The alternative hypothesis is sigma is not identity matrix. This test, this hypothesis are tested by Bartlett's test. Okay, this is the set of null and alternative being tested. Now, if you look at the output of the Bartlett's test follow chi-square distribution. So we've got a chi-square. So the chi-square tells us that chi-square is a large value, and the probability of getting such a large value at 36 degrees of freedom is very small. And so this chi-square is this value is very large value, which means that the probability of observing this data, probability of observing this chi-square value under the null is very low, right? It is 1.32 e raised to 97, so you have to actually put 96 zeros and then some number. That probability, really small probability. So if null is true, if the null hypothesis is true, that is, if population is an identity matrix, then observing this value for this sample is extremely less likely, which means perhaps this null is not true, and we say that alternative is true. That is, sigma is not identity matrix, which means that there are some numbers here, 0.2 in population, 0.4 in population, right? Those kind of things, right? So now, since it's not an identity matrix, we can do factor analysis. If it is identity matrix, then there is no common variance. So there's no point in doing factor analysis. That's the point. Yeah. Anybody else? See, this is what I was talking about when we spoke about KMO. And they've given cutoffs here. Kaiser's cutoff that KMO 0.9 is marvelous, 0.8 is meritorious, 0.7 is middling, and 0.6 is mediocre, and 0.5 is miserable. Yeah, so that's what they talk about KMO, right? Fine. So both these tests are telling us that we can go ahead and do factor analysis. Now, how to do factor analysis? I create new object called FA, factor analysis fit, right? There's a function in psych package called principal. This function. Okay. If you start typing, RStudio will give you a suggestion. That is this function principal from psych you want to use, princom, which is similar function in stats. You want to use, I want to use principal psych. Okay. Now, what will I put? I would put data one. Data one because it's a data of independent variables. Data one. Okay. Then I would write n factors. When I do factor analysis, I can extract as many factors as there are variables. So how many variables do I have? In data one, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 variables. It says data one here, 200 observations and 9 variables. So I can put n factor is equal to 9, right? N factors is equal to 9. And next is rotate is equal to, I will put 9. Okay. Now I'm using a method of factor analysis called principal component analysis. Okay. Now what is this principal component analysis? Let me go to I'm skipping some technical discussion. Yeah, this is very useful part, but we would look at it slightly later. So factor analysis uses two kinds of models. One is called component model. Second is called common factor model. Now this component model is useful because it extracts maximum variance and it retains unities in the diagonal of the correlation matrix as they are. Whereas common factor is not doing that. Okay. How and why we'll look at them more closely. Okay. In component model, the model of extraction is principal component analysis, PCA. Quite a few of you must have used PCAs. PCAs are methods used by Hotelling to begin with. It extracts maximum variance. The full model of the PCA is rarely used. We are going to use truncated solution. Right now, what we are doing is we are taking the full model. Okay. Now, in PCA, principal components are extracted from the correlation matrix. Now, how it works? It works like from the correlation matrix, we have a 9 by 9 correlation matrix. We have seen that correlation matrix, right? This is our correlation matrix. If you want to see it again, this is our correlation matrix. Yeah, this one is our correlation matrix, right? So this is a 9 by 9 matrix. I must say it's not 9 by 9. It needs to be 4, 8, 7. It will be 9 by 9. Yeah. Now this has become a 9 by 9 matrix, right? This is a 9 by 9 matrix. This is the matrix from which you extract principal component. So what you do is from this matrix, you extract first principal component. Now, what is a principal component in statistical manner is something that we'll discuss. Then once some variance is extracted from this matrix, so something is removed from this matrix, whatever is remains is called residual matrix.
Could you repeat the last few sentences, sir? There's some problem at your end.
Okay.
We couldn't
So
hear.
you remove first principal component from this matrix. Okay. Once you remove it, whatever remains is the residual matrix after removal of the first principal component. Right? Then you remove the second principal component. Then whatever remains is a residual. Then you remove the third. Then whatever remains is the residual after removing third. You keep doing it till you remove as many principal components as there are variables. We have 9 variables. You can remove 9 principal components. Every principal component explains some amount of variance in this correlation matrix. So if there is a 100% variance or there is a full variance, we call it 1. If the full variance is 1 in this correlation matrix, first will experience maximum variance. Second will experience lesser than first, but greater than anything after second. So third would be explaining lesser than second, but better than anybody after third. Fourth will explain lesser than third, but greater than fifth, sixth, seventh, eighth, ninth. Fifth will explain lesser than fourth, and so on and so forth. So as you keep extracting principal components, the amount of variance they would explain is going to reduce. If you total the amount of variance every principal component is extracting, that has to total to 1. That's the variance of the sorry. That's the variance of the correlation matrix. Since correlation matrix is in standardized form, the variance is always going to be 1. Right? So for every principal component, whatever variance it is extracting has to total to 1. Okay, fine. Let's try and do it. So I have written this function. You can copy it. I'm copying it. Is my voice still breaking, Shami?
No, sir, it's not now.
Yeah, my name is not sir.
Thank you. Thank you, Vivek.
Yeah.
It's not breaking now.
Yeah. So let's run this function fa_fit. Okay. Now I will, if I simply write FA underscore fit, no, I have written DA. So FA underscore fit, then this is the output that I get. Let me show this output to you. Okay. And there are few good learnings that we can have. So I'm taking this output from here to Excel so that things are easy to learn for us. See, these are our variables. This is first, second, third, fourth, fifth, sixth, seventh, eighth, ninth. All 9 principal components. These are our variables. So I'm putting, these are principal components. So I'm highlighting them in some different color. Right? Okay. Now, look at the first principal component. Okay. Now what I'm doing is I'm doing sum S cube, that is sum of squares of this principal component. Right? And then see, I've written sum of squares of this principal component. Pay attention. This is statistics that I'm doing, and I'm doing sum of squares of all principal components. Okay, fine. This is statistics. So I'm coloring it in some other color. Now, you know what? These things I'm slightly shifting here, and I do sum of squares here also. Sum of square of the row. Right? This is the entire row. You would realize that this sum of square is perfectly 1. It is just the rounding error that is making it slightly above 1. Otherwise, if you round it properly, it is 1. This is called H square. The software has already provided it here, right? So these are identical values. We can calculate it, or the software can provide it there. Okay. So this is the same thing. These are the ones that we calculate. These are the ones that have been already provided by software. So there's no error. Yeah. Okay. Now look at these sum of squares, and you would realize, let's now do the total sum of all of this. So sum of the column sum of squares. It is perfectly 9. It is perfectly 9. That is number of variables that you have. That is number of variables that you have. So I'm highlighting it slightly differently. Yeah. Slightly dark. Yeah. Right. So this is my total of sum of squares. Now, out of 9, how much is 2.629? That is this divided by 9, right? 29% or something. Now I do this across. You would realize this is percentage, but to convert it into percentage, I would multiply it by 100. right? So these are percentages. Look at first principal component. First principal component has extracted 29% variance from, so I can do the sum here. It has to be exactly 100, but again, the rounding error. Okay, fine. So the first principal component has explained 29.21% variance. Second is explained slightly less than that, but greater than anything that is after that. Third has explained slightly less than the second, but better than everybody else. And it is dropping down. You would realize that the as you go ahead, the proportion of variance that is left for the ninth principal component to explain is just 1.59, right? There's no much information that the ninth principal component is explaining, right? Only 1.5% information, whereas first is explaining close to 30% of the variance. Now I can actually plot all of them. Okay, I can actually plot all of them. So I take this and I paste here, paste, transpose, and paste, posto, paste values, paste values. Here means this, paste as a transpose. This is percentage. This is PC. And this data I can plot. This data I can plot. And it looks like there's a drop after the third principal component. So these are the first three, right? First has, again, I need to make it slightly better. Yeah. First is 29.21. Here it is, right? Uh, yeah. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 out of these. First three are having really large predictive capacities, and next three have comparatively smaller ones, right? This is in terms of percentages. But instead of plotting percentages, if I plot these numbers, sum of squares, right? They would also make sense. So instead of doing this in Excel, let me plot it in R, because we should also be able to plot these functions in R. Okay, so I have FAFIT, right? Now FAFIT is an object, and I need to know what are the various things in FAFIT. So I check names in FAFIT. There's so many things in FAFITs. One of the things is values. So I would do plot FAFIT, FA underscore fit dollar. Now inside FAFIT, these things are there, right? Inside FAFIT, so many things are there. So I would write FAFIT dollar values. Okay, and there's 1 to 9 numbers I need, right? This is the plot I need. On x-axis, numbers 1 to 9, and on a y-axis, FAFIT values, right? I'm running this. I've got these, but I want a line and dots both. So I would write type is equal to both. So I just write P, and I got line. Now I want the line to have a color red. So color is equal to, I would just write red. It has become red. But I also want these dots to be of different type. So I write PCH is equal to 16. And now the dots are filled, right? It's the same plot, but instead of here I took percentages, now I'm taking values. These values are called eigenvalues. Now, eigenvalues or characteristic values are nothing but column sum of squares, right? They're nothing but column sum of squares, right? So, this plot is typically called as Cattell's scree plot in fact analysis, or a scree plot. What is scree? When you are climbing mountain, suddenly the mountain becomes steep. So there is a gradual slope and sudden steep slope. So this is called a scree. Some authors call it elbow. So this is the elbow point of the hand. So this is your shoulder, this is your bicep, and this is your elbow. This is the elbow point, right? This is a forearm, if I have to perhaps talk about it like this. Okay, so this is the elbow. Anything above the elbow is what you retain. Okay, now I want smaller number of factors. You would realize that if I look at the factors that I have, first three factors have explained large amount of variance, 29, 28, 25. Next factors are explaining much smaller variances than the first three, right? Now, if you compare these variances, you would realize what we have obtained in R is a graph that shows that only first three are above the elbow or above the screen. So we should retain only first three factors, is what it is telling. So in factor analysis, we need to decide number of factors. We need to decide number of factors. The easiest way to determining number of factors is to plot this scree and then decide the number of factors. Okay, decide the number of factors, right? So how did we decide it? We plotted the scree. Anything above the elbow is the number of factors. So 1, 2, 3 is above the elbow. So this factor analysis will have three factors. Okay, this factor analysis will have three factors. Fine. Now, since we have decided the number of factors, we can redo this part. I'm just pasting this function for you in your chat box. Are you able to run these functions? Okay, that's great. Now, I am using the same function that I wrote, fa fit. Okay. But here, I would say n factors is equal to 3, which means I want to retain 3 factors. But I already have 3 factors data. See, if I kind of make the next factors invisible by making them gray. Yeah. I have 3 factors data. Right. I can look at 3 factors data. Who has stopped me from looking at 3 factors? Nobody. So let's look at 3 factors data. First principal component is every value now. So this is full solution. I was saying truncated and full solution. No. This solution, this matrix is called factor pattern matrix. This is a full solution. I need a truncated solution that is only this much. I found it out by using a scree plot. Okay. Now I need to interpret this solution. Let's try and interpret. Now here the logic is very simple. Anything above absolute value 0.3, absolute value 0.3 is something that we will take. Okay. So yeah, we have taken this. I'm making them bold. So yeah, all of them are absolute value 0.3 and above. This is also absolute value 0.3 and above. Everything. Now let us make meaning of principal component 1. Expenditure of food. So what is that? That is a part of principal component 1. Food. Oil is not much, so I'll kind of make it gray. Yeah, less than 0.3. Now 0.3 is an arbitrary cutoff. Fruits, petrol, bus, taxi, school fee, not paying school fee. Since they are negative, I'm saying not paying school fee, not paying tuition fee, not paying education fee. Who are these people who would not pay education, school, tuition fee, but would spend a lot on taxi? What is the meaning of this variable where people don't pay this? I don't see there's any meaning in this. Perhaps look at the second PC. School, those who are paying school tuition and education fees and spending on food a lot, but not spending on travel at all. What is the meaning of this expenditure? School and food expenditure without travel. This is school and food. नहीं, school and travel without food. भूखे रहो लेकिन नहीं, खाओ पियो, ट्रैवल करो बट स्कूल मत जाओ. यहाँ पे खाओ पियो, घूमो मत लेकिन स्कूल जाओ. यहाँ पे है खाओ पियो ट्रैवल करो, नहीं खाओ मत, ट्रैवल करो और स्कूल जाओ. ये कोई, this is not making any sense, right? This is not making any sense. Now, in order to make sense of this, I need to have a simple structure. What is simple structure? The problem is if you look at this data, you would realize classically what a psychometrician call cross loadings is what we are observing here. That is one variable, say food, expenditure on food, is loading on multiple factors. Fruits is loading on multiple factors. So there is no variable that is loading on only one factor. When a variable loads, that is, has a highest value on one factor and doesn't have much higher values on other factors, is called simple structure, right? So when we do factor analysis, we look for simple structure. Then why are we getting such a complex structure? We get complex structure is a extraction artifact. This is typically called as extraction artifact. We have used principal component extraction model, which extract highest variance in the first, second highest in second, and third highest in third. The variance is not distributed uh, theoretically, but it is primarily distributed in how much you can extract. That is causing trouble. Now we need to redistribute the variance. So we need simple, interpretable, and redistributed variance structure, right? How do we get it? We get it by doing what these people call rotations. Yeah. Rotations are done to get simple structure. They are done to get deal with extraction artifact, and there are two types of rotation: orthogonal and oblique. Let's not go there. Orthogonal rotations give us uh, uncorrelated factors, whereas oblique give us correlated factors. That's the only difference. Orthogonal, uncorrelated. Oblique, correlated. That's it. Let's go to R and do them. So we want three factors. The only change I'm going to make here is instead of rotate none, I will write one orthogonal method of doing a rotation, and that is at that is Varimax. I'll be free after 1 o'clock. Up to you. Okay, so I'm calling this fit1, FA fit1. Okay, I'm sharing this with you in your chat. Okay, Ishan said that it is academic oriented kind of factor for one of the three factors. He had some interpretation to offer. Okay, let's make it simple, Ishan, for you to offer interpretations. Okay, now I got FA1 with Varimax rotation. Okay, I have got the three factors. I'm going to paste them again in Excel, and I'll ask Ijan to give me a better explanation if it exists with this. Okay, Ijan, hold on. Text to columns. Finish. Okay. These are my three factors. So these are my rotated components. RC stands for rotated components. These are my variables, right? Look at what is most important. Okay, 0.3 and above. This is 0.3 and above, right? Here, this is 0.3 and above. This is 0.3 and above. Am I right?
Yes.
Okay. Now let us interpret RC3. rotated component 3. Expenditure on food, there is no expenditure, no oil, no fruit, no petrol, no bus, no taxi. Expenditure on school fee, tuition fee, education fee. What is this factor? Expenditure on
Education.
education. Education expenditure. That's great, Ijan. This is
Transportation.
transport expenditure. And last one,
Food.
food expenditure. Which of the two solutions look great? See, I post this next to this. Which solution looks simple? The rotated one, obviously. This is non-rotated. This is rotated. Right? Such a dramatic difference is brought. Now, is there a simple structure? Every variable is loading only on one factor, right? That's what we said when we simple structure, right? This is simple structure. Is this a simple structure? No, non-rotated is not a simple structure. Rotated, we got a simple structure, right? We have taken care of extraction artifact. Extraction से कुछ भी किधर भी गया था. Now it has been properly sorted, right? So rotated solution has given us an interpretability, which is interpretable. Rotated, non-rotated is difficult to interpret. So rotations provide us this great ability to deal with extraction artifact, absence of simple structure, and interpretability. This interpretability is so amazing and so simple. So we are going to use this solution. So what I can say now is, if you look at the predictor variables have got three factors, right? Predictors variables have got three factors. What are those three factors? Education expenditure, transportation expenditure, and food expenditure. That's it, right? Now, can I use these factors themselves as predictors? So I have got three factors. Can I use them as variables? I can, and that's the beauty of it. See, now, if I look at this function principle, and I'll ask for the help of function principle, it gives me an option. Here it is. Scores is equal to true. That is, find component scores. Okay, so it will find for every component the scores, and we can use those scores. So instead of just writing up till here, I would also write scores is equal to true. Now, right now we have fit one. If I write scores in front of it, this, do I have scores here? Yeah. Yeah, these are the scores. So I have scores available. Scores by default is true in fact right. The scores that fact analysis is saved. These are 200 values. That is our sample for RC3, RC1, and RC2. That is for every factor, for every person, we have got a score. Which means this can actually become a data frame, and I can save this data frame as PCs, right? Now, names PCs, RC1, RC3, RC2. Now, these names might be difficult to remember, so you can change names. It's easy to change names, but in the interest of time, I won't spend time there. Let us now use them as it is. We know what RC3 is. So RC3 is education. RC1 is transport. RC2 is food. Okay. Now, let's go back to our regression. Okay. It is the data that I have, right? The data is the data frame. So what I can do is I can create a new data frame. Data, say 2 is my new data frame. There is data dot frame is the thing that I will use, which will have data and which will also have PCs. Now, if I say names, data 2, I've got RC3, RC2, RC1, right? So I have got, this is my data 2, right? Fine. Wherein I have got rotated components in my data, right? So I have done something very, very interesting. I started with these 9 variables, that is food, oil, expenditure on food, oil, fruits, petrol, bus, taxi, school fee, tuition fee, education fee. And I have converted these 9 into 3 factors. This is, I know, is the expenditure on
Travel.
education. RC3 is education expenditure. Travel is RC1, RC2 is food, right? RC2 is food, yeah. So RC2 is food. This is one is
Education.
transportation. Sorry, one is transportation and 3 is education. Yeah, RC3 is education. Now, instead of writing a very complicated, long model, predictive model, which I have used, can I make it better and simpler model? I want to predict child insurance. And instead of writing all these variables, I just write RC1 plus RC2 plus RC3. And this is data 2. So first I will detach data, right? Because I don't want variable names to be overlapped. If I detach data, there's no data. Detach data 1. Okay. Data 1 was not attached only. And I will attach data 2. Okay. And this is the model that I have written. That and okay, this is what I have not shared with you. So I'll share with you. Right. Now this is the new model that I have written. So detach, attach, attach. So you can also run it. So now I've attached data 2. I run fit and summary of the fit. Look at this. the probability of investing in child's future education insurance is well predicted by RC3. RC3 is a factor of expenditure on school. Plus, some prediction comes from RC2, and RC2 is uh, expenditure on food. Okay, so this is the prediction that I get. Overall, the model explains 70% uh, variance in the dependent variable. That's amazing model. And there is very little difference in a multiple R square and adjusted R square. So, uh, well, there is this is a great thing. When the models are not written well, or when there is a lot of garbage in the model, then the difference in multiple R square and adjusted R square is large, right? Uh, see, it reduces. Generally, adjusted reduces. So from 72 to 71, but it is also still okay. Here, the reduction is hardly any. That's a great thing, great news. So I got a model which is better, which takes care of the problem of multicollinearity. I can do the same with parents insurance. Instead of writing so many predictor variables, I can use this, and I get the summary. Here, I realize that uh, the parents insurance is very well predicted by uh, RC1 and RC2, which is travel and food expenditure. So when parents end up spending more on uh, the school related expenditure of the child, parents are also likely to invest in the child's future education uh, insurance. But when they end up spending more on food and travel, then they are less likely to spend on uh, child's insurance, but they're more likely to spend on their own insurance. Is the learning we have from this data, right? We used factor analysis to reduce the number of variables. I could have perhaps just taken a factor analysis example, but I took this simply because it tells you that factor analysis is not just reaching to factors, but once you reach to factors, you can use factors as variables themselves. You can use factors as variables themselves, and that is a very insightful understanding that you get from these variables, right? And that's the reason why we use factor analysis to begin with in the regression models, because then it provides you the ability to reduce number of predictors to some sensible predictors, right? And that's how you use PCA in the regression models. But I could have done this for something else, and I'm going to get another data here and do that. And that data is the PhD data that I showed some time back. I'll, this is about understanding okay, I will now take this is a personality data, so I call it ERS data. What I'll do is I'll do just file.choose, and you are going to tell me what I should be doing. Huh? I'm not going to do anything. It's on desktop. Where should I click? PhD. I get this data, right? Now, what should I write? I want to do factor analysis of this data. Names, ERS data. Okay. क्या गलती हो गई? Oh हाँ, header is equal to true नहीं लिखा. नहीं, read.csv नहीं लिखा. Desktop. Names. I got these 6 variable names. Abhi, what should I do? Can somebody tell me quickly? I just want to do principal components.
Dim data.
KMO.
KMO, very good. Who is this?
Shami here.
Shami. Shami, tell me inside KMO, what should I write?
The data.
PERS data.
PERS underscore data.
That's great. Thank you, Shami. That's wonderful. So tell me, Shami, should I do factor analysis or I shouldn't?
0.56 come. Okay.
Nahi hai.
Nahi hai. You can do it, sir.
You can do it, Vivek.
Yeah, sorry. Vivek, you can do it.
Okay. Now, next I should do what?
The Cortes Bartlett.
Bartlett.
Bartlett. Yeah.
Bartlett test. Wonderful. So वो किधर गया? core.bartlett करके टेस्ट था ना? हाँ, ये वाला. So just core.bartlett. But my data is ERS data. You would realize that once you have set of codes, no, you just have to change things. You always need not write code. हाँ, ये p value बहुत छोटा है, तो क्या करे, करे या ना करे?
Yes.
Yes. What was the null hypothesis we have tested?
Identity. Summation is equal to identity.
Not summation. Not summation. Population.
Sigma is
correlation.
Population correlation matrix.
Sigma is equal to identity matrix. Population is equal to identity matrix. That's H naught.
Yeah. H naught is sigma is equal to identity, where sigma is a population correlation matrix, or population variance covariance matrix is equal to identity matrix, correlation matrix basically, not variance covariance. So this hypothesis is rejected, so we can do factor analysis. Okay, tell me what should I do now? What is the factor analysis command?
Principal.
Principal. Inside the bracket, what should I write?
The PERS.
PERS
underscore
data. After that, I
N
put comma.
factor.
N factor. Very good.
Now how
How
many variables are there that we have to see?
I have 6 variables. 1,
So
2, 3, 4, 5, 6.
6.
After
And
this,
rotate none.
very good. Rotate. I'm putting brackets because none is a word. Rotate is none. And this is to be stored, right?
Yes.
So I say fit 4 as the new object. Right? Should I run it?
Yes.
Anybody has any suggestions on this?
So assignment operator is not correct.
Yeah, thank you. Who is this?
Shami.
Shami. I'm not sure.
I just
Okay. We thank you for correcting this, Shami. Now we have fit 4. Should I type fit 4? Okay. Now, there are many things that we discussed. Can somebody tell me what is the meaning of first two? Or how many we need to retain? What do we need to do that?
We have to
How many
find
we
out
should retain?
some square and compare it.
हाँ, but वो एक्सेल में करते हैं ना.
हाँ.
यहाँ
Now,
पे क्या करें?
Screen plot.
Scree plot. Somebody said scree plot. I think it will work.
Yeah.
Yeah. So how do I plot scree plot?
Uh,
plot
Plot
Zero
within
RR
brackets,
plot.
1:9.
No,
dollar
not 1:9.
values.
Now how many variables I have?
6.
6. 1:6. See what 1:6 will do. See, if I do 1:6 here, no, it will only write 1 to 6 numbers. I'm just avoiding efforts of writing those numbers. Now, fit 4.
Fit 4. Dollar values.
Values, very good.
Type
This is
is
Shami, right?
type is equal to both in comma inverted
Type is equal to
both.
both.
B.
Then color
And
red anything and PCH is 16.
Color is equal to
Red or blue.
blue.
And comma PCH is 16.
Let's write 12 this time. क्या फर्क पड़ता है नंबर को लिखने का? करे प्लॉट. देखिए ये सिर्फ ये बदल गया. ब्लू का स्पेलिंग गलत है क्या?
It's COL, not COLOR.
Yes, COL.
CO.
L.
हाँ. हाँ हो गया कलर भी. थैंक यू सारिका. हाँ. अभी कितने फैक्टर है? स्क्री कहाँ पे है? एल्बो कहाँ पे आ रहा है?
2.
2 factors.
First 2.
2. First 2.
First.
Okay. तो अभी क्या? What should I write?
Now we have to print FA or fit 5.
Fit 5. N factor कितने लिखने अभी?
N factor 2.
हाँ. And rotate.
Vary max.
and scores is equal to T.
T.
Scores अभी हमको चाहिए नहीं because we don't have anything to predict. So let us not save scores. Let's run fit 4 on 5 only. Okay. Now we need to see what fit 5 is. ये fit 5 है. अभी मैं इसको तुरंत I'll just carry it to Excel sheet so things are easy to interpret. So these are my 2 rotated components. These are variables. Okay. Which should I highlight?
Point greater than 0.3.
Okay. So these and these, right? I'm not much interested in this right now, so I'm deleting this. Yeah. Now I'm giving you names for these variables. Okay. Adventurous. I've just written a shorter form. Okay. Please ignore the spelling mistakes if there are, or shorter forms. Okay. Can you tell me what is the meaning of RC1?
Neuroticism actually.
Neuroticism, or you to put it in simple words, all of this are indicating emotionality, right? These are all emotions: tense, worry, anxiety, and negative emotions. So I would say negative emotions or emotionality. What is this?
Extraversion, or we can call it sociability also.
Yeah, extraversion or sociability. Wonderful. So I can now use only these two factors to say that there are, instead of 6 variables. So this thing is called factor pattern matrix. Very useful a matrix. This is also called loadings matrix, and this has made my interpretation very, very easy. And well, what I have done is I have skipped a lot of technicalities of fact analysis in this. But I wanted to give you a practical solution of fact analysis. I could have gone to this PPT and would have made it more complex by saying that, look at some of these things, like variance component is aj square is equal to bj square plus cj square, where 1 is equal to h square plus a square, where a square is a unique component. Unique component is broken into uh, the unreliability and specificity. All of that I could have done. And we could have had a discussion like this, that how variance is broken, how h square is obtained, how zj, which is factor, is obtained, that is aij1 f1. Now what is zj? Look, this looks very complex, right? But zj is this. Zij is not this, sorry. Zij is data. So let's go to R. Yeah. If I, yeah, this 19 is Zij. I is this individual, J is this variable. This 19 is equal to, so when I say, look at this, 19 is equal to aij1. Aij is this value. First factor, okay, let's go here, yeah. Here, first factor for the first variable, aij square, so aij f1, first variable on first factor, plus aig2 f2, aig2, so now second variable on second factor, and so on and so forth. I keep doing this. This gives me this standard normal score. This is full model. With you, by using full model, I can recreate this data matrix. Okay, I'm not doing this technicalities because this is something that you should go and learn. I've kind of made it simple so that you remain interested in this and you develop some reason to go and learn factor analysis. The technicalities, well, there are a good amount of technicalities in factor analysis. So you basically take a matrix which is Green matrix. Green matrix is properties that data is unity is a square symmetric matrix. Non-unity is in the diagonal. the non-diagonal elements range from -1 to +1, all of that. To understand fact analysis well, what you need to do is you need to understand some amount of matrices. Some of you are from science background, some of you have done maths. So for them, it is hardly anything. So knowing matrix or even doing Cholesky decomposition of a matrix is pretty straightforward things for them. But those who have not done that amount of maths would provide this as an easy introduction. But my recommendation is go and do some basic maths and have a better understanding of fact analysis. Thank you very much. It is 1:10. We stop here. At 2 o'clock, we are starting again with Dr. Salunke's session. It's on the regression, and I'll be there in introducing him. Okay. Thank you very much. If you have any questions, please send them to me on the group. Since we are going to interact all 6 days, we will always have to bump on each other. So for my session, if you have any questions, you can always ask me anytime. And for other sessions, if you have questions, and if I know something in it, then I will answer. Okay. Bye-bye. See you at 2 o'clock at the same link.